In this example, we've been asked to determine the values of x for which the following series converges, remembering to check the endpoints of the interval of convergence. We have this power series here, the sum from n equals 1 to infinity, x to the n minus 1 over n times 3 to the n. So we start off remembering that to find the values of x for a power series, when a power series converges, we use the ratio test. For the ratio test, we need the general term, which is everything to the right of the summation sign. We call it un for a power series. So un in this case is x to the power of n minus 1 divided by n times 3 to the n. We'll be finding the ratio of un plus 1 to un, so it's a good idea to write down what un plus 1 is at this stage as well. So just taking un, wherever I see an n, add an n plus 1. So on the top line we will now have x to the power of n, all divided by n plus 1 multiplied by 3 to the power of n plus 1. We now state the ratio test. The ratio test allows us to find a value L, which is equal to the limit as n approaches infinity of the modulus of un plus 1 over un. When we introduce the ratio test, it's for positive term series. Because these terms now have a value of x which can be negative, the ratio test includes the absolute value of this ratio. So now we substitute the un plus 1 and un into the ratio test. We haven't taken the limit yet, so we continue writing the limit as n approaches infinity, substituting the two expressions in. The first one, un plus 1, we can write as a fraction here, divided by n plus 1 and 3 to the power of n plus 1. To divide that by this fraction over here, the expression for un, is the same as multiplying by the reciprocal of this fraction. So the n and 3 to the n come up to the top line, and we have the x to the n minus 1 on the bottom line. We need to take the limit of that whole thing, the modulus signs there. So we look to see what we can cancel. If we look at the x factors, we've got n x factors on the top and n minus 1 of them on the bottom. They're factors of this whole division and multiplication, and so all the x's on the bottom will cancel with all except for one of the x's on the top. Now the x value there has nothing to do with the limit n, so it can come out the front of the limit, and we'll keep the modulus signs around the x. What else can we cancel? We look to the factors of 3 here. We've got 3 to the power of n, so n factors of 3 on the top, n plus 1 of them on the bottom. So all those on the top will cancel with all of them except for 1 on the bottom, so there's a single 3 on the bottom. That also has nothing to do with the limit, so the 3 can come out the front. It's on the bottom line underneath the x. We've just got the n divided by n plus 1 left inside the limit now. We can't cancel anything there, so we write out our limit to see what we can simplify the limit as n approaches infinity, n divided by n plus 1. Note we don't need the modulus signs anymore. We know that n is positive. N is from our index of our summation. It goes from 1 to infinity, so it's positive, so we don't need the modulus signs here. To evaluate this limit, if we substitute in as n approaches infinity, the top line and bottom line will both approach infinity, so it's indeterminate. And so we evaluate that limit, or simplify the limit, by dividing top and bottom by the highest power of n, which in this case is just n. So the whole value of L is still modulus of x divided by 3 times the limit as n approaches infinity of 1 divided by 1 plus 1 on n. Now as n approaches infinity, we've only got one term of n. 1 over n approaches 0, so this fraction is 1 over 1 plus 0, which is a total of 1. And so our value for L, once we calculate this limit, is the mod of x divided by 3. So the ratio test tells us when the the series converges. We're interested in the values of x where the series converges. For the ratio test, L has to be less than 1 for convergence. So we can write that in there. So this value that we have has to be less than 1 for convergence. So that inequality can be rearranged to tell us the interval of convergence. We multiply up by the 3 will tell us that the absolute value of x has to be less than 3. And to remove the modular signs now, we know that x by itself will be in between -3 and +3. So we can rewrite that -3 being less than x, which is less than 3. And that tells us our interval of convergence. If we were asked for the ratio of convergence, at this point here, you could say the radius of convergence is 3. The question reminds us that we need to check the endpoints of this interval of convergence. The endpoints are where x is equal to -3 and when x is equal to 3. For those two values, you can follow your working back here, but when x is equal to -3 or +3, this fraction here would give us 3 divided by 3, which is 1, so our L value is equal to 1. The ratio test fails when the L value we get is equal to 1. So we need to investigate the convergence at these endpoints separately. So we let x equal these individual points and we go back to the original series and see what we need to do with that. So we split up these values separately. Over the side we write our first value, x is equal to -3. When we substitute that into the original series, we get this series here, the sum from n equals 1 to infinity. It's the whole of the x value is being raised to the power of n minus 1, so make sure to include the -1, divided by n times 3 to the n. This can be simplified by saying that that's equal to the sum of -1 to the n minus 1 times 3 to the n minus 1. So just splitting up this factors into -1 times 3 on the top line. That's all being divided by n times 3 to the n, which now allows us to cancel some of the 3's. We've got n minus 1, 3 factors on the top and n of the 3 factors on the bottom. So everything on the top will cancel and we'll be left with a single 3 on the bottom line. That has nothing to do with n now, so it can come in the front of the summation. And we get that's 1/3 times the sum -1 to the n minus 1, all divided by n. And we recall that this -1 to the n minus 1 term, we know that n goes from 1 to infinity. So this -1 to the n term makes this a alternating series. So we write down the fact we know that here. This is an alternating series. And for an alternating series to converge, we use the alternating series test. And so we require two things. The first thing is that an plus 1 needs to be less than an. And the other thing that we need is that the limit as n approaches infinity of an to equal 0. So we've got two conditions that must be satisfied for the alternating series test to converge. The 1/3 out the front is not going to change anything. If the series converges, then 1/3 times that series will converge. So let's investigate both of these conditions here. An for a alternating series is the general term not including the -1 to the n minus 1 term. So for an alternating series, an is just the term 1 over n. Using that, I can write down the expression for an plus 1. It's just 1 over n plus 1. To go from an to an plus 1, we increase the bottom line, which decreases the whole term, and so therefore we can see from that that our first condition will be satisfied. 1 over n plus 1 is smaller than 1 over n for all values of n. So our first condition is satisfied. The next condition we need to evaluate the limit as n approaches infinity of an, which is equal to the limit as n approaches infinity of 1 on n. As n approaches infinity, 1 over n approaches 0, so the limit we say is equal to 0. So our two conditions are satisfied, and so therefore at x equals 3, the series converges. So we will remember to include x equals minus 3 into our interval of convergence. That's the first endpoint. We must check out the other endpoint where x is equal to 3. So down here we write where x is equal to 3. Again, substitute that into the original series to get n equals 1 to infinity becomes 3 to the power of n minus 1 over n multiplied by 3 to the n. Straight away for that we can simplify something there. That's the sum from n equals 1 to infinity. Again we have n minus 1 factors of 3 on the top, n factors of 3 on the bottom, so there's 1 extra on the bottom. All those on the top will cancel, leaving 1 on the bottom line, and so we can take that 1/3 out the front of the sum again, and there we have it 1/3 times the sum, and all we're left with is 1 on n. Hopefully we can recognise this, the sum from n equals 1 to infinity of 1 on n, as the harmonic series, and we recall that the harmonic series diverges. So the total sum tends towards infinity. 1/3 of that total sum will also tend towards infinity. So all we need to say for this is that this is a harmonic series, and so therefore divergent. And so we will recall that x equals 3 is not inside our interval of convergence. So at the end we summarise everything, write down the original series, the sum from n equals 1 to infinity of x to the power of n minus 1 divided by n times 3 to the n converges for the x values, which are negative 3, less than or equal to x, which is less than 3. You can see we have included negative 3, x is equal to negative 3 is inside the interval, and x equals 3 is outside the interval. You could also write this using some other set notation, saying that x is an element of the set, which is from in between negative 3 and 3. It includes negative 3, so we use a square bracket. Does not include 3, so we use a curved bracket. Open set, closed set on the left hand side, open on the right hand side. So that shows the values of x that will make the series converge, including the endpoints.